Our next talk of the session is Dr. Francisco Lagunas Vargas, who is currently a postdoc at the Applied Materials Division at Argonne National Lab, who specializes in studying extremely beam-sensitive samples, including in a material system that was new to me and I'm quite interested to learn about, which is 2D transition metal carbides. So let's learn about those.
All right, everyone. I'd like to start out by thanking the organizers for this session or for this workshop for inviting me to come talk here today. I've been working on this material system for a long time now, pretty much since the beginning of my PhD. And so I'm pretty excited to share a lot of these results. So if you haven't heard of MXenes, they're a family of two-dimensional transition metal carbides and nitrides. They were first synthesized in 2011 by a group at Drexel University. What they discovered was that if you take a parent max phase material, this is a layered ceramic, you can selectively etch away the A element in this material using pretty high strength hydrofluoric acid, and then produce these suspended 2D sheets. Now, the use of hydrofluoric acid during the synthesis results in the introduction of these surface groups, which is usually a mixture of oxygen, fluorine, and hydroxyl, and is commonly abbreviated in TX. Like most other 2D materials, these MXenes are held together by relatively weak van der Waals forces. And so by simple mechanical agitation or other exfoliation methods, you can go from these stacked sheets down to a few even monolayer flakes. Now, the beauty of MXenes, or what kind of separates them from some other families of 2D materials, is their large range in chemistries. So at the time that protocol was discovered, there were over 60 known max phases at the time, and that quickly translated to the synthesis of a large family of MXenes with different metal groups. Now, this was at 2019, so 8 years after the discovery. And even though there was an expansion in the different metal groups that you could have these materials made out of, the surface groups were still pretty much limited to oxygen, fluorine, and most recently to chlorine. And that has to do, and that's despite there being significant interest in tailoring these properties. Because there was a variety of theoretical work that showed that if you could change the surface groups of these materials, you could actively tailor their properties and introduce new effects. So I had the privilege of working with the Talipin group at the University of Chicago, where they were experts at using Lewis molten salts in order to synthesize a different variety of nanoparticles. And they used this molten salt in order to etch away the A element of this max phase group and produce a MXene with just a single type of surface group, in this case, bromine. So my job as a microscopist was to acquire cross-sectional images of these materials in order to confirm that they had the expected structure. And then using nanoscale EDS mapping, we could confirm that we had indeed uniform surface coverage of just these bromine terminations. Now, what's exciting about this bromine-terminated MXene is that the surface groups on this material are bonded a lot less strongly compared to oxygen or fluorine. And you can see that reflected by the enthalpies of formation for titanium bromide. What this opens up is the ability to do different chemical substitutions of the surface groups by using relatively simple chemical processes. So you can go from these bromine-terminated MXenes to tellurium-terminated MXenes, those terminated with sulfur, selenium, and imido terminations, so NH2. And you can even remove the surface groups altogether and have these bare MXenes. Now, I looked at a lot of these materials along these cross-sectional views, and we started seeing some interesting effects resulting from the introduction of the different surface groups. So if you look at this M perpendicular spacing, which I'm calling the spacing of titanium, the top and the bottom titanium along the basal plane, you can track this spacing for a variety of different surface groups, and you see a general trend that as you get to heavier surface groups, this M perpendicular spacing decreases. If you combine this with measurements of the in-plane lattice parameter from XRD, you can start getting an idea of the different types of strain effects or lattice distortions that these surface groups induce in this material. And in the case of the bromine and tellurium terminated, these strains that we have in the material are actually really, really large. Now, the even more exciting part was, in addition to changing the structural properties of these MXenes, introducing different surface groups actively change their electronic properties. So if you have an niobium carbide MXene, and if you terminate it with oxygen or remove the terminations altogether, you can cool the material and you do not see a superconducting transition, whereas if you terminate it with sulfur or selenium, you do see these materials undergo a superconducting transition. So that really motivated us to try to explore further the different ranges of surface chemistries that we can understand in the MaxEnes. So today I'm going to be talking a lot about a new family of MaxEnes that we're calling hybrid MaxEnes. These are MaxEnes with, instead of a single species of surface groups, have a single organic molecule that bonds, or amine that bonds to the surface. And the range of different amines or surface groups, organic surface groups that we can have is quite large. So we show them in that blue right there. Now, okay. So really quickly, I want to go through some of the main findings of this study, and then focus more on some of the work that we had to do to characterize these hybrid materials. So the first interesting thing we saw was when we terminated these MaxEnes with organic surface groups, we saw the emergence of a Finot resonance in IR spectra. And this occurs from the coupling between the vibrational states of the organic surface groups and the continuum states of the titanium carbide itself. The other, a little less flashy, but equally important, or I would argue more important result, was that when you introduce these surface groups are hydrophobic, and so they actually keep the material from degrading underwater for significantly longer periods of time. Before, when I would get these samples, I'd have to look at them within a few days of their synthesis in order to get really nice images, because otherwise they degrade really quickly. But the surface groups here really help stabilize the material. Okay, so this material is pretty challenging to look at. And the reason is because it's composed of two primary components. So you have your titanium carbide, and then you have your organic surface groups. And each of these components degrade differently under the electron beam. So I have these little scale bars. And typically when you want to look at materials and avoid knock-on damage, you reduce your accelerating voltage, let's say down to 80 or 60 kilovolts. And then if you want to look at things with organic material that degrade by radiolysis, you typically want to increase your accelerating voltage so that you can reduce the likelihood that you have some beam interactions. Here I had to kind of strike a middle, so we ended up going with 200 kilovolts. The other challenge is the electron dose that you use to look at these materials, and then the sample temperature. So in general, you want to reduce the amount of electrons that you put into your sample, but since this is a scanning electron microscope, you collect more signal with the more electrons that you put into it. So you have to strike a balance between getting as much structural information as you can from the material while also not damaging it heavily. And then we'll talk a little bit more about sample temperature in some later slides. So how do we actually look at these materials? How do we take a sample that looks something like that in the SEM image and then start getting these atomic resolution images from it? Well, the biggest consideration is going to be sample thickness. So you have these big stacked sheets that look like accordions, and they can be quite large. And if you take something like this and put it in the microscope, there's no way you're going to be able to resolve it. So what people often do is they prepare different Fib samples from these. So they take this particle, they put it in a focus ion beam, and then they take out a lamella. And these lamellas have a lot of structural information for the material. So here you can see we have kind of the expected contrast that we would have, where we have these bright titanium columns or layers, and then between those layers we have a strong carbon signal, which is where organic material would lie. And then if you look at the annular bright field images from this material, you can see we have these nice resolved columns, which correspond to the titanium carbide. And then between them, we have very poor contrast, which is from the organic material itself. The Fib lamellas also show quite a bit of interesting defects. So if you looked at the low magnification image I showed earlier, there's a lot of nanoligamentation, like it's coming apart. And then if you zoom in, you can start seeing things like these ripples or these like Y-like forks or these X forks where you have two layers come together and merge and then separate out into one another. Now, this is great, but preparing Fib samples takes a lot of time, expertise. And in the case of these samples can often get damaged through the Fib preparation itself. And if we want to look at a lot of samples, we need something that we can go through more samples more quickly or prepare samples more quickly. So what people in the community typically do is this relatively simple procedure where you take your Maxine powder, you disperse it in either water or some sort of alcohol, then you sonicate it in order to start ripping away layers of these Maxines. You let it settle so that the heavier particles can go to the bottom, and then you can take off just a few droplets from the top surface, and you get something like what I show here. So this is a very dilute Maxine sample. We have like few to even monolayer regions, and I put some white lines in there so you can start kind of identifying the individual flakes. These samples are pretty delicate. So this is at 200 kilovolts, and we're looking at like it along the C direction, so like just a flat view of these sheets. And all of these little holes are beam induced. So it's very hard to look at these materials when they're very thin. So what I was interested in doing is looking at the cross sections of these materials. And eventually you find a protocol where you have not quite like a very dilute sample, but instead you get something where you have maybe 5 to 10 layers of these Maxines. And you start looking for what I'm calling these single folds or these nested folds. So a single fold is you have a sheet of Maxine that's folded over on itself, and you could look at this cross-sectional part along the edge here. You can see an individual Maxine. Or a nested fold is where you have maybe stacks of 5 to 10 Maxines that then fold on themselves. And then at the edge here, you can start resolving the atomic structure of these materials. Now the question, or when I first took this image, I was super excited. Because you can see the titanium columns are really clearly resolved. And then between the contrast from the titanium columns, you see a little bit of periodicity. And it turns out that periodicity actually comes from the fact that we're looking at a folded region. So you're not only picking up the organic material, but you're picking up the Maxine that sits on top and below it. And we're pretty confident that that's what that comes from. Okay, so now we have to be really careful with our electron dose. So we have our materials that have these organic surfaces or organic surface groups on them. And we know that these organic materials break down rapidly under the electron beam. So what you typically do is find a region and then start doing consecutive scans to start understanding the evolution of this material under different beam exposure conditions. So we'll start out with 1,000 electrons per angstrom squared. We can see we really nicely resolve the atomic structure of this material. And then if we do another scan at about 6,000 electrons per angstrom squared per second, we start seeing the introduction of this kind of like rippling pattern, these like little wiggles that start forming. If we go to something crazy high like 20,000, you'll start really destroying the material. So you're like actively reducing the contrast that you see from the titanium columns, either just from knock-on damage from the beam, or you're like slightly misorienting the sample from so much electron source. So we thought we found a kind of a sweet spot. So this is for images of these Maxines at 2,800 electrons per angstrom squared. And you can see between scan 1, scan 2, and scan 3, there appear to be relatively few differences. And that was honestly kind of surprising because 2,800 electrons per angstrom squared is actually a lot of electron dose, especially when something has organic material. But nonetheless, we kept looking at these samples. So here's a few of the different chemistries that we saw. And basically, we have longer and longer surface groups that we're introducing here. And we tend to saw that if we had larger surface groups, those little wiggle or ripple patterns that we saw tend to be a little more pronounced. Now, when we compared our SEM analysis to XRD measurements by our collaborators, we saw that something was not quite right. So if you look at the XRD lattice parameter for the 002, which is the basal plane spacing here, the XRD measurements are consistently larger than those that we arrive on for STEM. So we decided to test or to probe our sample a little more by looking at electron energy loss spectroscopy. And in particular, we wanted to look at our carbon K edge. Because if we were looking at our material, and this carbon organic material is in its pristine state, we would expect to get a different electron energy loss near edge fine structure. So we would expect to see different spectra based on that. However, when we ended up doing these measurements, so on the top spectra there, we have our Maxine with our organic surface group. In the middle, we have just our MaxScene, and then on the bottom, we have amorphous carbon as a reference. You can see that the MaxScene by itself has more fine structure than that of with the organic surface group on it, which indicates, or which led us to believe that the surface group was being amorphized under the electron beam under these dose conditions, even though we really didn't see much of a change. And the reason that we didn't see much of a change is because it happened way earlier than the conditions that we were imaging at it. So here's one of the most extreme samples where we have a really large interlayer spacing. And you can look at images that we acquired with less than 10 electrons per angstrom squared per second, about 100 electrons per angstrom squared per second, and about 400. And if you look at this basal plane spacing, you can see that at lower dose conditions, this spacing is larger. And then as you start applying higher electron dosage, that you see a small compression of these layers. We can quantify this a little bit more. And so here we're showing this 002 spacing, which is that same basal plane spacing I talked about earlier, under a variety of different dose conditions. And you can see by the time we get our microscope in conditions that we would see atomic resolution imaging, we had already seen the majority of this compression. And this compression happens pretty over a large range of areas. So it's not like we see our nice sheets and then all these like compressed areas. It happens over the entire folded region that we're trying to look at. So for that reason, we turn to cryogenic EM, or in situ cooling. So this is one of the knobs that we have as microscopists, is to cool down the sample temperature. And at lower temperatures, the materials tend to be a little more stable under the electron beam. Now, this comes with some trade-offs too. So this is the kind of holder that I use to cool these samples. And basically what it is, it's a big metal rod with a cold liquid nitrogen tank on the end. And you can imagine as that metal rod cools down, you're going to get some thermal contraction. And then even after it cools down entirely and is at a stable temperature, you have this boiling container of liquid nitrogen that's going to introduce quite a bit of vibration into your imaging. So just, I have a couple of videos. And this is me on the microscope looking at the liquid nitrogen levels. And on the right there is kind of an image that you would get. This again is you're at liquid nitrogen temperatures, but even with stable temperatures, you still have a lot of thermal vibration in the material. And what you really need is something like this, where you can see the liquid nitrogen level is sufficiently low that you have very low vibration, but not low enough that the whole heater is going to start, or the whole sample stage is going to start heating up again and expand. This really reduces your window of imaging. So you can go from loading in your sample, finding the best spot, optimizing your probe, and that'll take you some time, and instead limits that whole, or the window that you can get really nice atomic resolution imaging down to about 20 minutes. So I was some tough times as a grad student. Okay, so if we look at all of our MaxScenes and compare this interlayer spacing at room temperature and at cryogenic temperatures, we can see in general that for those with relatively shorter spacing, so what I'm calling under 20 angstroms, we have really good agreement with our STEM results and our XRD results. Whereas the measurements of these, the same measurement at room temperature showed a pretty systematic lowering of it. There's kind of a cutoff around that 20 angstroms, where even if you cool the sample down, you still see a pretty big difference between the XRD results and your imaging at cryo conditions. And this likely comes from like the harsh vacuum conditions that the microscope column is under. It's pretty harsh for these organic surface groups. Okay, so what about our EOS measurements? So I said earlier that the carbon structure in our organic surface groups should show up nicely in our carbon K-edge measurements. So here's a measurement of that same sample at room temperature and at liquid nitrogen temperatures. And you can see now we're starting to have a lot more features in our carbon K-edge. If we look at two samples that are particularly different, we have our benzylamine terminated MaxScene and our butylamine terminated MaxScene. One of them has a lot of carbon double bonding while the other one doesn't have any. And you can see in the spectra, especially between, let's say, 286 and 290, the shape of the one with a lot more carbon bonding really is more flat, whereas the one without any double carbon bonding is sloped upwards. And so you can see the contribution from that bonding show up in the eels. Okay, so the exciting thing was we have our material we know what kind of dose conditions it's relatively stable at, or at least organic material isn't amorphizing. And now here is what happens when you go beyond that dose threshold. So we're imaging it. Now we give it a lot of dose, and you see it kind of wiggling all over the place. And if we let this keep going, eventually you'll see the material start kind of tearing apart. You can see these like Y forks and some similar defects that we saw earlier start populating. And then eventually it'll saturate along there, yeah. So what's happening? So we think what we're observing is the formation of what are called Ripplocations. So Ripplocations are kind of what the name suggests. They're these like nanoscale ripples that form in layered materials. And there was a nice work published in Nanoletters where they took MOS2 and they actually touched it with a probe, and then they induced the formation of these wrinkles. And you can see that this looks very similar to what we're seeing in our sample. So we think that we're inducing these types of Ripplocations with the higher electron beam exposure. A little more, so these Ripplocations are, they're kind of like a dislocation vector, but in layered materials, the insertion of an extra atom or the exclusion of an extra atom results in this bending-like structure. And they're energetically different than dislocation vectors, where as you have dislocation vectors of the same sign will repel one another, Ripplocations will actually attract one another. And so we didn't see this at room temperature because we're amorphizing the surface or the material between these Maxine layers and kind of effectively locking them in place. Whereas at cryogenic temperatures, we have these layers, and then we're still damaging it, even at low temperatures, and we're knocking out the organic material between them, and it allows us for the observation of this vibration. So here's some comparison to some theoretical work of this done on graphene. And what I want to highlight here is they show what the effects of different defects are in the material. So here they have a vacancy that forms. And if you remember some slides earlier, I showed that when we look at these materials at 200 kV, we're actively forming knock-on damage. We're actively forming vacancies. And so it's likely that the combination of these Ripplocation formation and these vacancies that ultimately leads to the saturation of this material. Okay, this is probably my favorite slide. So I was looking for these Ripplocations in these other Maxines. Here's a Maxine that shows really good agreement between the XRD and the cryogenic stem measurements. So we have it close to its pristine structure when we start looking at it. And you can see at the low mag image, we have a couple of these bumps, so these ripple-like features in the material. There's also a tear, and you can see we're in a folded region, so it's pretty messy with what's going on there. But this cool feature happens where if you look at this first ripple, and the image C there, you can measure the peak of that ripple from where there's a fourth layer on the material is about 40.4 angstroms. And then if we do another scan, we can see that ripple actually migrates over to the left here. I found another reference where they were looking at these Ripplocations in, I think it was polysilicates. And their little graphic of the Ripplocation actually matches really nicely with what I observed, where you have some ripple, and then it says that moves laterally like a ripple, and we can see that directly in some of the STEM images. Finally, if we start out with the material that is slightly degraded when we start out, we have a little more range of control with the type of defects that we can introduce into this material. So this octylamine terminated Maxine is, even at low dose conditions, the spacing is smaller than than XRD measurements, and so the material is already slightly degraded by the time we put the beam on there. But what that allows us to do is it increases the range of electron dosages that we put on before we induce even more noticeable electron effects. And so we can do these really little individual bend defects on the material. So just to kind of wrap up, this type of bending Ripplocation defects happen over a large range of different layered materials. So we can get down to the few nanometers. I showed in some of the fib lamella, we saw similar features around maybe 50 to 100. People can do this kind of on a benchtop by like taking steel cards and putting them on top of one another and then compressing them, and you can get this ripple-like features. And then you can actually see it in layered systems, such as in the Earth's core, up to hundreds of nanometers. So the fact that we have this defect that we're looking at from scales of nanometers to like hundreds of meters is really exciting. And why do we really care about these defects? Well, the Maxines are trying to transition between being in the lab and making it out into real-world technologies. And one of the most promising applications for Maxines is as electromagnetic shielding, and particularly in extreme environments. And we saw here that our Maxines deform differently at different temperatures, particularly at low temperatures. So it's important to kind of understand all the subtleties of these materials and how they deform under a wide range. Okay, how long do I have left?
A minute or so.
Okay, just with the last minute, I just want to thank Argonne National Lab for allowing me to come here and share this work. At Argonne, like I said, we're trying to take this material and take it outside of the lab into a variety of different applications. And so we have this Argonne Maxine Innovations, where we're actively trying to tailor Maxines for applications in catalysts, as well as coatings, or as well as energy story applications. And the beauty of the National Lab System is that we have access to a variety of different experts, either in scale-up, nanoscale characterization, and modeling, and so on. And then with the last 30 seconds, I have a kind of a self-promoting slide. So next year, I'll be starting a research group at Washington University in St. Louis, and I'm actively looking for graduate students and postdocs. We're going to have a fancy new microscope and be able to do some really incredible work. So I'm really excited for this, and if you're interested, please let me know. Cool. And with that, I'll put the acknowledgements and take any questions.
All right, thank you very much. That was really cool. And may I just say, I stand in awe of whatever chemist thought of molten cadmium bromide as an, oh my God. Do we have any questions? I have a question. So the ripple features that you observe, these are in folded sheets. Have you ever seen two of them actually merge and annihilate the way it was suggested?
Not quite. So we're really limited by our electron dose modulation. So the thing that we're using to image it is actively changing the properties of the material. I suspect with a lot more precise like dose control, we can definitely see features like that. But for the time being, we haven't been able to.
Well, the reason I ask is it's tempting to think of this as a cross-section, but it's not really a cross-section, right?
Yeah.
It makes me wonder if what you're looking at are actually bubbles, because the mass that is being removed from the termination molecules is not ceasing to exist, and presumably it has a lot of trouble diffusing out, especially at the lower temperatures. Is there any reason to think those are not bubbles moving around inside?
So we have a couple of different scenarios where we've looked at them. So like in this case, the bubble would be, I guess, trapped above it instead of below it. So that the bottom region is, sorry. Let me try to go back a few. Okay, so at least in this example, so if you're suggesting there's a bubble forming at least below the ripple and that's what's leading to it, like the vacuum is below the layers there. Yeah, okay. It's a pretty messy system. So I kind of prefaced that earlier. We're in a folded region, but the fact that we're in a folded region seems to suggest that it's Ripplocations, because in order to form these types of defects, you need compressive strain on it. So we think that strain is arising somehow from the fold on the material.
Presumably what you're losing from these molecules is going to be very light elements, hydrogen, nitrogen. Presumably it can't be the amines or they detach, but do you have some idea for which elements are actually departing during this amorphization?
Not quite. So we have a couple of experiments where we want to try looking at the spectra, the EO spectra, at different dose conditions. And we should be able to pick up differences in, there we go. We should be able to pick up differences in the type of bonding that we see as a function of dose, and then understand at higher dosages what kind of bonds break first.
All right, very cool. Does anyone else have a question they want to ask before we move on? No, okay, then let's thank our speaker one more time.